the business of detecting the mouse in the maze. This is a remarkably difficult thing to do, it turns out. I guess I thought it was going to be easy, but it turns out not to be. We have some requirements, and the first of those is that we must have better than 1 millisecond timing resolution. Races have been won and lost on milliseconds in difference, 10 milliseconds or so. And so it's important that the timing system has good resolution and is reliable. There must also be low latency, because whilst it's easy enough to detect, well, it's not easy enough to detect a mouse, but once you've detected a mouse, you don't want some arbitrary delay between the detection and the recording of the time. If you had a delay, so long as it was consistent, that would be fine, but ideally it should be very low. We have issues with ambient light. So those of you who were at Hazelmere a couple of sessions ago may recall the marching sunbeam that went across the room and made its way towards the maze timing system, and we were busy juggling the curtains to try and stop the sun shining on the sensors. In APEC, a couple of APECs ago, we were right by a big loading bay, and there was enormous amounts of light pouring in, and we had to, during the runs, test runs, we had to wait until it got darker before we could do it. So all these things are not good. And of course, one of the biggest sources of interference are the robots themselves, which pump out huge amounts of light at the most inopportune moments. So all in all, there's lots of things that kind of get up in your way of getting this right. And above all else, it's got to be easy to set up and use. So the options for different kinds of timers, different kinds of sensors, turn out to be fairly constrained. Mechanical, electrical, and acoustic, and radio or radar, they all really not very, very practical. I have run in a contest that uses ultrasonic sensors. It wasn't great. They stick right, or in that case, they stuck right out into the cell, and they were just a big nuisance. So in the end, you're pretty much constrained to some form of optical sensing. You can try and bounce light off the mouse, or you can try and have the mouse break the sensor beam. And when you have a look at what that means in practice, that too turns out to have some issues. This is a side view of the UKMARS bot, and you can see that it's quite a complicated object. There are shiny bits, there are dark bits, there are holes and gaps, and bits dangling around all over the place. So you have to kind of try and take that into account. Are you looking for something to go dark? Are you looking for something to go light? What happens if it goes dark and then light again? The robot ideally will be going through quite quickly. So that's another issue. You don't want a system that can detect the mouse reliably, but takes so long to do so that it's been and gone by the time the job's ready. And of course, a mouse may stop halfway through, either by accident or because of a crash or because it thinks it's in there, in the cell, gone through the gate or whatever. And you wouldn't want a timing system that reacts adversely to that. So if it was self-adaptive, for example, it wouldn't want to think that that's the new normal. So if we try and reflect light off there, we have a few options. David Otten presented some stuff to us a few years back in 2009 and 2010, and his first sensor used a reflective setup, which I believe, I didn't ask, he can tell us later maybe, I believe was simply like a conventional mouse sensor. So you shine a light out, you measure how much comes back, and you use that to determine whether the mouse is there. He said that the sensitivity was adjusted so that it didn't normally see the wall, and any change, darker or lighter, would be the mouse. The following year, he talked about an upgrade where he used his PSD sensors to detect the mouse. These are much nicer in that they are much less dependent upon the ambient lighting conditions. So he would measure the distance to the wall on the other side of the gate. And if that distance changed, then something had gone through the gate. Dave's skills in building these things far exceed mine. And they require specialist devices which are not cheap or necessarily easy to get. The lenses in particular are difficult. And so that's not something that I really particularly wanted to do. If we try and shine light across the gate and measure the mouse going through it, this is perhaps the most reliable method. Unfortunately, you need something either side of the gate, and that can cause alignment issues. And you, generally speaking, have to get at those devices from underneath the maze. Salviano can tell us later who this is, but I'm not picking on the Portuguese. This happens or has happened in the past. I have pictures of Tony Wilcox under the maze. In Japan, in Japan, they mount them before laying down the maze panels because they're flat on the ground. In Taiwan, they have to get to them from underneath, and it's altogether just a nuisance. The sensors they use in Japan and Taiwan, however, are quite good, but then they would be because they're not cheap and they are designed for the job. These are commercial industrial light sensors. They come in pairs. The actual fiber pair is £137 in the UK. Each pair has to be connected to an amplifier. That's £180. So you're talking £600 or £700 worth of equipment just for one start gate and one stop gate. And I venture to suggest that that's somewhat outside our budget, even if we wanted to be poking stuff up from underneath the maze, which I would really rather not do. So if we want a transmissive sensor, which is intrinsically going to be more reliable, then what else can we do? Well, I should have said, by the way, that the transmissive sensors are synchronous. That is to say, they flash the light on and off, and they detect the differences between the two. The Portuguese system does that, and I believe the Omron sensors do the same thing. What we could try to do is to shine a constant light across the gap. We wouldn't need any connection or any communication between the two sides, because one side would just be a light shining all the time. And then we could use software to detect changes in illumination levels, and use that to determine when the beam's been broken, rather than rely on some kind of synchronous detection. Blue light is now readily available, and most mouse sensors are likely to be fairly insensitive to blue light, so that's a good thing. If you use too narrow a beam, like a laser, though, you have an issue with pointing the thing and being reliably on target on the other side of the gap. So with a very narrow beam, you have to be remarkably accurate. On the left-hand side, those narrow beam diagrams, those are only 4 degrees. So if you're off by more than 4 or 5 degrees, you're just going to miss the target altogether. A wide beam will be much more forgiving. Although it does look pretty awful, it looks like you've got a floodlight shining out on the maze. So what about the mouse itself in these configurations? Well, as long as the mouse is traveling orthogonally, neither the sensors nor the gate sensors will be too likely to interfere with each other. The forward-facing sensors can get blinded or affect the gate sensor. We've had that in UK contests with poor collimation of the gate sensor, killing a couple of mice, and we had to reconfigure the maze so that people could get through it reliably. And in a diagonal configuration, there is always a point where the mouse sensor is looking right down the throat of the gate sensor and vice versa. So you have to take that into account. And even if your mouse isn't traveling diagonally, it's going to be turning. And at some point, trust me, it's going to be looking right into that sensor. And you really don't want it to be blinded. So with a wide beam and blue light in a darkened room in the privacy of your own home, this is what it looks like. It looks a bit scary. It's kind of bright, but you'll see that I could be quite some way out in terms of illumination, in terms of pointing the sensor, and still get a reasonably good signal on the other side. In more normal lighting, it doesn't look nearly so bad. And in competition lighting, you probably would hardly see it at all. But it is a little alarming when you see it for the first time, how much light is flooding out. My mouse sensors certainly are largely unaffected by this. I haven't been able to kill the mouse going through it, so that's good. There would normally have been a whole bunch of stuff about the makeup of the sensors themselves, but I'll content myself with a picture of the assemblies. The detector shown in the middle, sorry, the emitter shown in the middle is simply an LED with a current limiting resistor. I've got some surplus cell phone batteries. They're about 800 milliampere hours. They last all day. The circuit board on there is just a 5-volt DC to DC converter and charge controller for the lithium cell. Little on-off switch, job done. It all sits inside a conventional common plastic maze wall. The slot in the PCB is because I couldn't dig down far enough to get rid of the internal ribs in the maze wall, so it just slots over that. At the top, the emitter, at the top, the detector has the same battery arrangement, a little Arduino micro, which looks at the photo transistor and does a bunch of software to let it determine when the mouse has gone through. Also connected is a radio transmitter, and there's a little array of resistors which set the address. And you can have up to 16 of these detector gates in one radio environment. So it should be possible to run multiple competitions at the same time using the same gear with relatively little risk of interference, and a single central receiver could detect them all, probably. One day, perhaps, we'll find out. So the active devices in there poke out through a hole in the end of the wall, and then they come out through the posts, which are made up into 2 diagonal parts in the manner described by Bird, and they can be arranged so that you either shine right through or you reflect at 90 degrees in whatever direction you like. You can simply turn the post around and get the beam out wherever you want it. To make the reflector, the best material I found is the shiny wrapper from Sweets. It's like a metallized plastic film. Aluminium foil is not very good. You get too much diffuse reflection. Detection of the edge is all done in software. You get a signal, a noisy signal, almost certainly, of varying intensity. And if you filter it twice, once with a very slow filter and once with a slightly slow filter, and take the difference between those, the white line you see at the bottom shows you when the signal has a step change. This works remarkably well, and in tests I can detect a matchstick dropping through the gate every time, and I figure that's probably accurate and sensitive enough, and it will do that even with a fairly large amount of ambient illumination. Battery life is good. They look bright, but they have to run at pretty inefficiently. That is to say, the detected signal is a few tens of counts in spite of my best efforts, partly because of the wide beam spread, partly because of the diffuse reflection, partly because of the convoluted optical path. Overall, I think I would rather go back and try and make a better reflective design, maybe using a photodiode to give me better dynamic range, and a faster processor so that I could do better signal processing on the whole thing. As part of the testing, I made a sensor blaster, and the sensor blaster consists of a 555 timer, which shines out 1 kilohertz low duty cycle pulses. These are very similar to the kinds of pulses emitted by a mouse, and it all just sits on top of a surplus Christmas tree light battery holder. It just pumps these out continuously. It's enormously bright, and for those of you with a mind to, it's a bit like a TVB gun, but for mice. If you left that hanging around anywhere near the maze, mice would be crashing all over the place. So this is used to make sure that the timing sensor gate works even in the presence of lots of interference without having to have my mouse drive back and forth through it all the time. And thus far, I have not been able to place that in a position where it prevents detection of something going through the beam. So in that regard, I would call the whole thing successful, but I would still like to make some improvements. And of course, I would really very much like to actually try it in a contest.